In the last video, we looked at the reactions of our carboxylic acid functional groups. Carboxylic acids, of course, are widely important both in biochemistry and in organic chemistry, and they have a wide range of different reactions that they can use. Now, one of those reactions that we looked at led to the formation of our esters, right, where we had the carbonyl of our carboxylic acid and the oxygen of our carboxylic acid, but then this oxygen was attached to an additional carbon chain instead of to the hydrogen in our carboxylic acid. Right, so this makes our ester, and our ester represents our first example of a carboxylic acid derivative. So our carboxylic acids can be converted into a range of other carboxylic acid derivatives. All of them will share the same key structure of a carbonyl attached to an electronegative atom, represented here by S. So today we're going to be looking at the varieties of different carboxylic acid derivatives that we can form as we change up that particular atom there. The first carboxylic acid derivative that we'll look at today is our acid chlorides. So in an acid chloride, our extra electronegative atom is a chlorine. So we have our chlorine here attached instead of the hydroxy group of our carboxylic acid. For our acid chlorides, we're going to name these as alkanoyl chlorides. So instead of that oic acid ending, we're replacing that with essentially our OYL ending instead of the OIC ending. And then of course we have the chloride there, indicating the presence of our chloride in our molecule. So as we look at this example acid chloride shown here, so of course our acid chloride is going to take priority. So this will be carbon 1, 2, 3, 4, 5, and 6. So our parent chain then is our hexane or hexanoyl chloride then, as we add in the suffix for our new acid chloride functional group. And of course we need to indicate our alcohol functional group here. We name that as a substituent. This is a 5-hydroxy hexanoyl chloride. Our next carboxylic acid derivative is the acid anhydride. So with our acid anhydride here, you can see our electronegative group is actually an oxygen bonded to a second carbonyl. So it's almost like two carboxylic acids sandwiched together with a single oxygen instead of their two different hydroxy groups. Our acid anhydrides will be named as alkanoic, again using the OIC ending of our carboxylic acids, but then with anhydride added at the end to indicate that we have our acid anhydride here with our two different carbonyls. So again, that OIC ending, that's just indicating our oxygen here as usual with our carboxylic acid, and the hydride indicates our specific functional group. Again, we'll look at a specific example here. So with our acid anhydride, of course, we have two different alkyl groups on either side that we need to account for. This is a symmetrical acid anhydride, right, and that both of our groups are the same. So we can use one name to indicate both of our groups. Both of our groups have 3 carbons, so we're going to look at this as two different carbon chains that both have the same number of carbons. So this would be propanoic anhydride. If we have an asymmetrical anhydride, then we would just have multiple alkanoic names in front of our anhydride to indicate the names of each of our individual acid anhydride alkane chains. So those will be a little bit more complicated. Those are relatively rare. It's somewhat difficult to work with asymmetrical acid anhydrides just because then you're always going to have multiple products with any reactions that you have with our anhydrides. So kind of similar to asymmetrical ethers, right, where that asymmetry kind of leads to some problems in terms of our selectivity as we're undergoing our reactions. So symmetrical acid anhydrides would be much more common, but of course our asymmetrical can be named just by adding an additional alkanoic name there to indicate that other carbon chain. Our third carboxylic acid derivative is, of course, the ester that we saw in our previous video. Again, esters, of course, still have that oxygen of our carboxylic acid, but they have a carbon chain attached to that oxygen, similar to our ethers, whereas our carboxylic acid would just have the hydroxy group there. Esters will be named, again, somewhat similar to our carboxylic acids, but we need to add a new component for our carbon group here attached to our oxygen. So as we go to name our esters, so our carboxylic acid portion over here is going to be named similar to our carboxylic acid. So this would be an alkyl group, and we would end it with a OATE ending. Alkanoate. So we're again switching up our ending here to indicate our ester functional group as opposed to that OIC ending that we use for our carboxylic acids. But then we need an additional name here for our carbon chain on the other side of our ester functional group. So this is going to get a separate, it's going to be named as a branch, an alkyl branch in front of our ester functional group with that O8 ending there. Again, looking at a specific example here, so we have our alkyl group off of our ester that we'll name first. So we have our 3 carbons here to make this a propyl group. Now we go over and name our ester itself over here. So we have our 4 carbons, so this is going to be a butanoate, but of course we also have to add our bromo branch here. So looking at our ester carbon as our first carbon here, this is at the 3rd position, so this is going to be propyl 3-bromo, and then our butanoate with that OAT ending indicating our ester here. So the bromobutanoate, again, indicating our first portion here, and the propyl indicating the carbon group coming off from our ester functional group. The final carboxylic acid derivative that we'll look at is our amides. Now, our amides use our nitrogen as our electronegative atom attached to our carbonyl. And of course, the unique thing about nitrogens is that they can have 3 bonds due to their 5 valence electrons. So we end up with 2 different carbon chains that can be attached to our nitrogen in addition to our carbonyl. So in our naming here, we're going to have to indicate each of these carbon chains. And in our, what we're going to do is we're going to add an N in front of those names. So it's going to be a N alkyl, indicating each of our alkyl groups attached to that nitrogen, and then our alkanamide to indicate our actual carbon group and the amide that are attached together there. So it's an N alkyl, alkanamide. We use an amide ending there to indicate the presence of our amide functional group. So in our example shown here, we have our amide here with our carbonyl and our nitrogen. We have our 2 different alkyl groups attached to that nitrogen. We have a methyl group here with that single carbon. We have an ethyl group up here. And then of course we have our main chain here with 5 carbons, and this would be a carbonyl group at our 3rd position, which we name as an oxo substituent. So let's start off with our alkyl groups. So this is going to be N-ethyl, N-methyl, and then we have our 3-oxo, and this is a 5-carbon amide, so it would be a pentanamide for our full name there of our rather complicated amide structure. Amides, as you can see, are a little bit more complex because of those multiple possible carbon substituents that we can have off our nitrogen, in addition, of course, to whatever complexity we have on our main parent chain. So at this point now, we can name all of our different carboxylic acid derivatives. But the question is, what makes them unique? Well, of course, as we look at our carboxylic acid derivatives, the key difference is always going to be in that new group that's attached to our carbonyl. So the properties of our new group will determine how our reactivity of our carboxylic acid derivative will change. So the key is going to be how electronegative is that group is, right? Because that will shift the overall electron distribution within our molecule. And then also how good of a leaving group is it, right? If we have a good leaving group attached there, it's going to be more likely to break off, which will then lead to interesting new reactions for our carboxylic acid derivative. So our individual carboxylic acid derivatives can be ranked according to their overall reactivity. At the top we have our acid chlorides. These are the most reactive. Then we have our acid anhydrides. Followed by our esters. And followed by our amides as the least reactive of our carboxylic acid derivatives. Now, in order to understand this reactivity ranking, we of course need to take a closer look at our overall structures. Let's start down here at the bottom with our amides. So of course, as I already mentioned, one of the key factors is going to be electronegativity. Nitrogen as our least electronegative of our possible attached groups here will make it less reactive. The other key thing to look at here is the resonance within our carboxylic acid derivative. Since our nitrogen has relatively low electronegativity, it can donate its electrons in order to shift our double bond. So if we complete that resonance structure, we would end up with our nitrogen with the double bond and our oxygen now with an extra lone pair and a negative charge. Our nitrogen will have a positive charge in this case. Now, in this case, right, this will be a minor resonance contributor because we have our two formal charges here where we have 0 formal charges in our original structure. But our oxygen is more electronegative and is getting the negative charge, whereas our nitrogen is less electronegative than our oxygen and it's getting the positive charge. So this is still a fairly significant resonance contributor because we're able to give more electrons to that more electronegative atom. Let's compare this to our ester. So if we do the same thing with our ester, our oxygen decides to share those electrons in to give our carbonyl oxygen more electrons. In this case, we end up with our negatively charged oxygen up here, and our oxygen down here now gains a positive charge as it shares in that lone pair. Again, this will be a minor resonance contributor, and in this case we have a positive charge on our oxygen. So while our oxygen will share some electron density in, so we can share electrons between our two oxygens, this will be a more minor resonance contributor compared to our amide. So that makes our amide more stable, right, because of that extra electron sharing there, which again makes it less reactive. Right? Less reactive also corresponds to more stable. Right? The more unstable we are, the more likely we are to react. The more stable we are, the more unlikely we are to react. So nitrogen is less reactive here in our amide, both because of its lower electronegativity and then because of the increased resonance we have here as that nitrogen is able to donate in our electrons. Now, as we look at our top two carboxylic acid derivatives, we can use some similar reasoning here. So with our oxygen here and our acid anhydride, this guy is kind of split between two different carbonyls that are both pulling electron density towards themselves. Right? So these both want to pull in that extra electron density. and this oxygen is kind of sandwiched in between, and it can't have as much of a stabilizing effect on either of those carbonyls. Right? Here our oxygen can just be focused on helping to stabilize this carbonyl. Here it's kind of forced to split between the two. Another way of looking at this is if we break our acid anhydride, let's say we were to break this bond here, our other half would now form a carboxylate where we have this negative charge that can be easily stabilized by resonance between our two oxygens. Again, of course, resonance stabilization of our product means that we're going to be more likely to react to create that more stable product, and so our original reactant then becomes less stable and more reactive. So our acid anhydrides tend to be quite reactive compared to our esters and our amides. Now finally, if we look up here at our acid chloride, so we have a couple different things going for us to make our reactivity quite high up here. First off, remember that our chlorine is a great leaving group, right? Chlorine is very happy to exist as our chloride anion, right? So it's relatively easy for this to break off and then allow our carbonyl to react to create new compounds. But the other thing is here too, if we follow the same resonance reasoning that we use for our other compounds, right? If we resonate with our acid chloride, we get a negatively charged oxygen and a positively charged chlorine with a double bond to our carbon. Well, halogens in general don't like to make double bonds, right? They often don't have very good overlap between their larger p orbitals and the smaller p orbitals of our carbon. So it doesn't really want to give up its electrons. It also doesn't really form a very stable double bond. So this is a very minor resonance contributor, again, contributing less overall stability to our acid chloride compared to all of our other carboxylic acid derivatives. So that, combined with the fact that our chloride itself is a very good leaving group, makes our acid chlorides the most likely to react of all of our different carboxylic acid derivatives. All of these will use fairly similar reactions. So that reaction that we saw between our carboxylic acid to make our ester, we'll see very similar reactions with all of our other carboxylic acid derivatives. So that will be something that we'll be looking at in our next lecture.